Can you rebuild a tree from just its travel diaries? Construct binary tree from preorder and inorder traversal is a pattern mastery 100 cornerstone, regularly asked at Amazon, Apple, and Google to test your deep understanding of recursion and tree building. Over 35% of candidates miss subtle index bugs or don't manage recursion boundaries right. Let's break it down so you don't. We'll use the basic method to solve construct binary tree from preorder and inorder traversal, giving you a powerful template for any tree reconstruction problem. Let's break this down. Given two arrays representing the preorder and inorder traversals of a binary tree, with no duplicates, reconstruct the original binary tree. Input: preorder, nodes visited as root, left, right. Inorder, node is visited as left, root, right. Output: root of the reconstructed binary tree. Here is a real-world example. Imagine restoring a company's org chart from two different reports, one listing employees as visited in order of management, preorder, the other listing them by their department or hierarchy, inorder. Interviewers might ask, how would you reconstruct a configuration or parse tree if you only had two traversals? Let's assess. What's tricky? You must know how preorder and inorder traversals uniquely determine a tree. The first value in preorder is always the root. In inorder, everything to the left of the root is the left subtree. Everything to the right is the right subtree. Think step by step. Use a pointer or index to track the current root in preorder. Use a hash map to quickly find root positions in inorder, to split left and right. Recursively, pick root from preorder. Find its index in inorder. Recursively build the left subtree, from inorder left split. Recursively build the right subtree, from inorder right split. Advance the preorder pointer at each recursive call. Let's clarify. Always slice the inorder array to define subtrees. Preorder's root pointer moves forward every time you build a new node. Base case: if there's nothing left to build, left index greater than right, return null. Edge cases: empty lists should return null. Single node builds a leaf. Deeply skewed trees, for example, all left or all right children. Here is the structure. Build a hash map of value index for inorder for O1 lookups. Create a recursive function with left/right boundaries for inorder. At each call, use the current preorder index for the root value. Increment preorder index for the next call. Recursively build left subtree, inorder left split. Recursively build right subtree, inorder right split. Return the constructed node. Now let's implement the recursive construction using an inorder index map, allowing us to rebuild the tree efficiently in linear time. We begin our solution class, which contains the tree building logic. This method reconstructs the entire binary tree using preorder and inorder traversal lists. If the preorder list is empty, there's no tree to build. So we simply return none, an empty tree. We create a dictionary that maps each value in the inorder list to its index. This means we can instantly find the root's position in the inorder traversal instead of searching linearly. This optimization is why the entire solution runs in ON. This inner function builds a subtree using only index boundaries, no slicing lists, just moving pointers. If our preorder or inorder range becomes invalid, it means there are no nodes left to construct in this subtree. So we return none. The subtree is empty here. In preorder, the first element in any valid range is always the root. We create a new tree node using that value. We quickly find the root's index in the inorder list to determine how many nodes belong to the left subtree. The number of nodes in the left subtree is everything between the inorder left boundary and the root's index. We recursively build the left subtree by shifting preorder to the next element, taking exactly left_size nodes, using the corresponding inorder left range. Then we build the right subtree by jumping ahead in preorder past the left subtree, using the remaining preorder range. Using the inorder range to the right of the root index, we return the constructed root node, now connected to its left and right subtrees. We start by passing the full preorder and inorder ranges so the entire tree is built from the top down. And that's how this algorithm works. It first creates a fast index map to locate roots instantly, then recursively partitions preorder and inorder ranges to rebuild the left and right subtrees. Efficient, simple, and elegant. Let's test our recursive solution with these traversals. The preorder array tells us the order in which nodes are visited as root left right. The inorder array tells us how nodes appear as left root right. From preorder, the first value 3 is the root of the entire tree. In the inorder array, 3 splits the list into left side, 9, this is the left subtree. Right side, 15, 20, 7, this is the right subtree. Using the inorder index map, we can quickly find where each root appears. For the left subtree, Preorder gives us 9 next, that becomes the left child of 3. For the right subtree, 20 becomes the root from preorder, and 15 and 7 become its left and right children respectively based on the inorder split, 15, 27. Putting it all together, the tree we reconstruct is root, 3. Left child, 9. Right child, 20. Left child, 15. Right child, 7. Which corresponds to the level order output, 3, 9, 20, null, null, 15, 7, and that's exactly what our function returns. The reconstructed tree matches the expected structure perfectly. So, our implementation is correct. The recursion plus inorder index map rebuilds the tree in linear time and passes this test case smoothly. Now let's implement the iterative stack-based method, reconstructing the tree step by step while maintaining preorder-driven structure. We begin our solution class containing the iterative tree building logic. This function reconstructs the binary tree using iteration and a stack. If preorder is empty, the tree has no nodes. So we return none immediately. The very first value in preorder is always the root, so we create a node for it. We place this root node onto a stack. This stack keeps track of the path of parents as we construct left and right children. This pointer walks through the inorder array to determine when we should stop building left children and start attaching right children. We iterate starting from the second preorder value since the first one made the root. For each new preorder value, we create a new tree node. Here's the key idea. If the top of the stack does not match the current inorder value, that means we are still going down the left subtree. So we attach this new node as a left child of the current stack top. And we push this new node onto the stack because future nodes may attach beneath it. Otherwise, the top of the stack equals the inorder value, meaning we finished building that left subtree and must start attaching right children. We repeatedly pop from the stack while its top matches the current inorder value. We store the pop node in last. This is the node that will receive the right child. We move forward in inorder since we've used up this node's inorder position. Once we stop popping, we know the new node must be the right child of the most recently popped node. We push the new node onto the stack so future nodes can attach beneath it. Finally, we return the root node, representing the fully reconstructed binary tree. And that's how this algorithm works. It first uses preorder to decide the creation order of nodes, then uses a stack and inorder pointer to determine when to attach left children and when to switch to right children. Efficient, iterative, and elegant. Now let's test our iterative stack-based solution with the simplest possible tree. Both traversals contain just one value, -1, which represents a single node tree. In the iterative method, we start with the first value of preorder, which is -1. This becomes the root node. We push this node onto the stack. We also track an index into the inorder array. Since inorder 0 is also -1, it confirms that this root has no left or right children. It's just a single node. No additional nodes are processed, no extra attachments are needed. The final tree is simply a root with value -1. This corresponds to the output, -1, and that's exactly what our program outputs, -1, perfectly matching the expected result. So, our implementation is correct. The stack-based approach cleanly handles even this minimal case, confirming the logic works for single node trees as well as larger ones. Rebuilding a tree from its travel diaries sounds tricky, but with preorder and inorder you've got a perfect roadmap. This is a classic interview favorite because it exposes whether you truly understand recursion, boundaries, and tree structure. Let's do a recap. We're given two traversals of the same binary tree: preorder, root, left, right, and inorder, left, root, right. The goal is to reconstruct the original tree. Think of it like restoring an org chart from two reports, one in visit order, one in hierarchical order. We leaned on two core truths. The first item in preorder is always the root, and in inorder, everything left of that root is the left subtree and everything right is the right subtree. The main pitfalls? Mismanaging indices and not respecting subtree boundaries as recursion unfolds. Our plan: create a fast lookup from value to its position in the inorder list. Use a moving position in preorder to pick the next root. Then, with left/right bounds in the inorder range, recursively build the left subtree from the left side of the split and the right subtree from the right side. Stop when the current inorder window is empty. We followed that blueprint, advancing the preorder position each time we formed a new node and using the inorder boundaries to keep each recursive call in its lane. No extra slicing work, just clean boundary management. We ran the solution on LeetCode. It constructed the sample tree correctly, handled empty input as null, built a single node tree for the one-element case, and coped with skewed trees. All tests passed without errors and the logic behaved exactly as expected. The big lesson: Tree reconstruction is all about disciplined boundaries. Anchor each step on preorder's next route. Let inorder define the left/right regions, and let recursion do the assembly. Get the indices right, and the entire tree falls perfectly into place.